Hello, Mr. Melo here, your online math teacher, and welcome to my channel. Today we're going to be kicking off my series on exponential functions and logarithmic functions because they're really tied hand in hand together. So if you find this video helpful, please consider smashing, breaking, destroying that like button, and subscribing, and check out some of my other videos. So we're going to kick it off by talking with exponential functions, which you might have seen before. So let's start by considering the definition of an exponential function. And we are going to say an exponential function is the exponential function with base b that is defined for all real numbers x, defined by some number a times b, where we're raising b to some power of x. So we're plugging in the powers for it. So, that's what we're plugging in. And we're going to put some constraints on a and b here. And we are going to say a is non-zero because otherwise, no matter what I plugged into x, I'm multiplying by 0 and it's not an interesting function to study. We're also going to require that b be greater than 0 because that when it's less than 0 or a negative number, it's going to do kind of funky things. And we're also going to take the convention that b is not going to be equal to 1 because 1 raised to any power isn't going to be that interesting to look at either. So let's take a moment to look at a table and look at some graphs of exponential functions. So I have f of x is equal to 2 to the x. So I'm just raising 2 to different integer powers to fill in my table. And similarly, g of x, where I'm raising 1/2 to these different integer powers to get points on my graph. So try pausing my video and seeing if you can fill in this table yourself. Okay, hopefully you tried it, and if you did, you got the following. And by taking some of these nice points on the graph, you can sketch a rough picture of it. So in our case, if I graph f first based on those points, I'll get the following picture, where you can already extrapolate from the points. When I get more and more negative on my numbers, my values are going to get closer and closer to 0. So it's good practice to draw in that horizontal asymptote that's going to be taking place at y is equal to 0. And then you could do the same thing with this function g here to get a similar curve. So these are what our functions f and g look like, and I have them color-coded. So we got g of x over here, and we have f of x on the opening up to the right. Now, just a little fun thing here, the way I set up f and g, you can express them as a transformation of themselves. So I can write the function g of x as being equal to 2 to the negative x, because the way I distribute my x to both the 1 and the 2, because it distributes with a fraction, I can bring the 2 upstairs by making it a negative x. And then this is just the same thing as looking at f of negative x. So these two functions related by a transformation. In this case, it's a reflection over the y-axis. Now, our graphs of these exponential functions can look a little different depending on our choices of a and b. So we really have 4 different pictures that we can get depending on if we're letting a be positive or negative and b be bigger than 1 or between 0 and 1. So in the case where a is bigger than 0 and b is also bigger than 1, you are going to get a function that looks roughly like this. When a is positive but b is smaller, so between 0 and 1, then that's when you're going to get a picture that flips over the y-axis and looks like this. And that's just what we saw in that example up top that we just graphed. In the case where we make a negative, if you think back to transformations of functions, a being negative means you're adding an additional reflection over the x-axis. So that means when a is negative and b is between 0 and 1, we're just flipping this second picture over the x-axis too. So you're going to get something like this. And then finally, if I make a negative and b being bigger than 1, you are going to end up with a picture that looks roughly like this. But one thing all these pictures have in common is that their domain is going to be all real numbers. So that's what my little r here means. But the range will vary, as we see in these pictures. The range will vary. And another thing they have in common is that the line y is equal to 0 is a horizontal asymptote of the function for all these cases. Now, if you start translating our graph up and down, we're going to change where that horizontal asymptote is, but we're not talking about that right now. So, one nice thing about these functions, if we're just looking at an exponential of the function that's a to some power of x, then we don't need too many points to identify what it is. So, if I have one of these examples like here, if I know 2 points on the graph, I'm good. And in fact, I really only need one of them. If I'm not shifting it all around, 0, 1 is going to be a point on all these exponential functions graphs if I'm not translating it. So what I'm looking at is a second point on it. If I know the point 110 is on it, on my graph, then if I need to find a, I know 10 is equal to a to the first power, which is just a. So you would know your function is equal to 10 to the x. Similarly, if I know 2 1/4 is a point on my exponential functions graph, then I can say, well, if 1/4 is equal to a squared, because that's what I get by replacing x and y in a sense here, the value I know when squared gives me 1/4, that's positive because I know my graph has all positive numbers, is going to be a being 1/2, because 1/2 squared is 1/4. So that means your function is just 1/2 to the x. So that function we graphed a little bit earlier. Now, it's nice to be able to cover your equation from very few points, but a more common thing you're going to need to do is graph transformations of them. Now, the first step in graphing any transformation of a function is knowing its base function really well. So in this case, since I want to graph a transformation of 3 to the x, I need to know a couple nice points that I can transform on it. So for instance, here's the base function. So I have 2 nice points I picked out on the graph because I know the general shape, and I have an asymptote that I can move. Now, whenever you do your transformations, I recommend writing a list of step-by-step instructions you're going to use to move the asymptote and move the points to get the graph we actually want. So in this example, because I always recommend the mentality of working inside out when making your list, the innermost part of our transformation is going to be dealing with this x plus 1 up top. So the first thing in my list is going to be a shift to the left by 1 unit because of the plus 1. The next thing you can see working inside out is this negative that's in front of the 3. And a negative in front of our base function means a reflection over the x-axis. And the last part of our transformation that you always deal with is your vertical shift up and down, or vertical translation if we want to use a little bit more rigorous terminology. So this minus 1 out front, which tells me I'm going to shift everything down by 1 unit. And then we can apply this to our asymptote and the points on our function. So the asymptote, I always recommend starting with, if you have one, or any other unique part of your graph. So if I shift my asymptote, or this line at y is equal to 0 to the left 1 unit, it's not really going anywhere. It's staying on itself. Again, if I reflect it over the x-axis, because I'm on the x-axis, it's still not going anywhere. But when I go to shift it down 1 unit, that does move the line. So our asymptote, by the rules we just wrote, is moving to y is equal to -1. So this is the first piece we have. Now we can apply our list to those points. So I'm going to start with this point at 0, 1. If I shift it left 1 unit, I'm moving here. Then I need to reflect it over the x-axis and then move it down 1 unit to get its final location being here. I can do that to my point at 1, 3, shift it to the left 1 unit, then reflect it over the x-axis and shift down 1 unit. And I end up here. And then based on the shape I knew I had beforehand, I can fill in what my graph is going to look like. And I end up with this picture. So it's not a bad picture of a transformation. So you just need to know a couple nice points or features on your graph or of your base function, and then make a list of step-by-step instructions to transform it. But you need to be comfortable with the base functions first. And the last thing you might end up doing with exponential functions early on is talking about compound interest. And a compound interest is a formula just like I have here. A of t, which equals the value after t years, or maybe you're working in another time unit. It could be months, days. It really depends on your problem. P, which is the principal investment, which in terms of these types of problems means what is the amount invested or amount put into something at time equal to 0, at t is equal to 0. R expressed as so R is the interest rate, but we need to make sure we are expressing it as a decimal. N in this is the number of times interest is compounded per year, or whatever time unit you are using. So it might be months, days. So you need to be consistent there. A of t, t has to be consistent with that. How many times are you compounding in 1 unit of time? And finally, t, as I've been saying this whole time, is the number of years or a similar time unit. It might make more sense to talk about months or days, especially if you start looking at problems that aren't finance related. And we can use these compound interest problems to figure out questions like here. So if you're investing $500 at an interest rate of 4.5% per year, which if you find a bank account that's going to give you that per year, let me know, because that's a really good percent. Then find the amount in the account after 5 years if where interest is compounded annually, semi-annually, quarterly, monthly, daily. So this is just changing the number of times it's compounding on that interest within that year. Annually is just once a year, semi-annually twice, quarterly 4, monthly 12, and daily 365. So the only thing that's going to change for each of these things is the n, the number of times compounded per year. So for instance, in the annual one, we're going to, in our formula, which I have up here, this n in the bottom's 1 for annual, and the n in our exponent is 1 as well. When I go to semi-annual, that is going to change to a 2 in both those spots. Quarterly, a 4. Monthly, a 12. And daily, a 365. And when you do this, and these are typically calculator problems, you'll plug this whole bit of jargon into your calculator and get the following. And you can see by looking at the difference that the more times a scenario like this is compounded, the better it is for you. You're going to make more. Now, there's a lot of instances where you'd want it compounded less. Unfortunately, when you have student loans, they're going to be compounded daily by companies. So that'd be an instance where it hurts you to be compounding it more frequently. So I hope this video helps as a good introductory to exponential functions. So like this video, check out the next video in the series, and have an awesome day.